Hello, calculus fans, and welcome to section 3.4, where we cover the chain rule. The chain rule is the most widely used differentiation rule in calculus. So it's an important one, and it does take a little bit of practice to get the hang of it. So let's get started. Well, so we know how to differentiate a function like this, where we just have the, sine of x, or x squared minus 4. But what if we combine these in a way like this, like f of x equals the sine of x squared minus 4? Well, this function is a composite of two functions. So you could have, remember in maybe an algebra class, you'd have f of g of x, or maybe you'd have this like fog, right? Fog and golf. I don't know if you guys have seen that before. This is actually a lot better notation, because this one, when you have a composition of functions like this, it's looks like what it is. Like I'm plugging this function g into function f. This f circle g or fog has to kind of be explained, so I like this notation better. But they're both out there. So with the chain rule, when we take the derivative of something like this, we have to consider two things. Not only do we have to consider the rate of change of the sine function, but we also have to consider the rate of change of this inner function, the input to the sine function. So there's a little, the chain rule says right here, the derivative of the composite of two differentiable functions is the product of their derivatives evaluated at the appropriate points. And there's two ways that we can think of that, and I'll show you both ways. But first, let's look at an example here. So we've got an easy example, right? So it says y equals 6x minus 10. Now we could easily find y prime, right? Y prime is just 6. But let's break this up into, force it to be a composition of two functions. Like, we could say, well, this is really equal to 2 times 3x minus 5. And of course, we wouldn't really do that, but this is just to show you an example of a chain rule, so you'll see it that it seems reasonable, right? So this would be the composition of two functions. Composition of two functions. Because it would be like this: y equals 2u, and u equals 3x minus 5. All right, so if we really wanted this to break it up into a composition of functions, we could do it this way. And then let's find the derivative of y with respect to u. Right, so the derivative of this with respect to u, which is just going to be 2. And then also the derivative of u with respect to x. So if I take the derivative of this u with respect to x, we just get 3. And then let's just look at this one. If we started here and said y equals 6x minus 10, so if we just found dy dx, right, from here, we're going to get 6, right? The derivative of y with respect to x is just 6. So if we look at this right here, dy du equals 2, this means that the rate of change of y is twice as fast as the rate of change of u. Right, and also over here, if du dx is 3, that means that u changes 3 times faster than x, right? Because the rate of change of u with respect to the rate of change of x is 3, so u changes 3 times as fast as x. So then what about this? If y changes twice as fast as u, and u changes 3 times as fast as x, what if we compared y to x? Wouldn't y then change 6 times as fast as x? And then if you look over here, that's what it says over here. It says dy dx is 6, so this is saying that y changes 6 times as fast as x. So the question is it true that we could say dy dx equals dy du? times du dx. So, I mean, it's true here, but is this a general statement we could make? So that's the question we have to investigate. So to see, let's take a look at another example. For this example, we could definitely just take the derivative and find y prime just using the power rule. But also this one factors. So let's say if you take a second and see if you can factor this. It's like a quadratic sort of, but it's a fourth degree, but it will factor kind of like if this were a square and x to the first power. And it turns out to be, it's a perfect square trinomial. So what we want to do is take a minute and see if you can fill in the blanks and then check back. Okay, so hopefully what you did, you tried it out. You notice, well, if I put a 3x squared here and a 3x squared here and a 1 and a 1, and a plus and a plus, then if I do the FOIL method on here, I get back here. So in other words, this is really equal to 3x squared plus 1 squared. Okay, so let's force this function to be a composition of functions just so we can investigate that chain rule idea that we had above, where dy dx seemed to be equal to dy du times du dx. So for this one, let's think of this as a composition of functions where we have y equals u squared and u equals 3x squared plus 1. Okay, so then if we had dy du times du dx, we would get, well, dy du, the derivative of y with respect to u, that's just going to be 2u by the power rule, right? That's equal to 2u times, then we look at du dx. You come over here, the derivative of u with respect to x by the power rule is going to be 2 times 2, which is 6x. So you multiply these two together. And then we've got this u here, right? This u we need to deal with. Well, here's u right here, because we want these to be in terms of x. So I'm going to, for this u, I'm going to write that there. So we get 2 times 3x squared plus 1 times 6x. Well, of course, multiplication is commutative, so order doesn't matter. I can move these around. So 2 times 6x is 12x. So let's write it like this. Then if I distribute the 12x through, we get 36x cubed plus 12x. So dy du times du dx is this. And the question is, does this equal dy dx? Well, let's go back here and just say we were going to take this derivative originally, the derivative, and we say dy dx equals, we use the power rule. So you get 4 times 9, which is 36x cubed. And then we have 2 times 6, which is 12x. The derivative of 1 is just 0, so that doesn't matter. And we get the same thing. So it appears that dy dx equals dy du times du dx. So what we've just demonstrated is actually the chain rule. And the chain rule just says that dy dx is equal to dy du times du dx, where y and u are the composition of functions like we did here. And it almost looks like, if you treat these as differentials, like you could cancel these, right? So it sort of looks like that anyway. But this is basically the chain rule. This is one of the notations that we'll use. There's a couple notations that we'll consider. This is probably the more standard one. But I think there's a one that's a little easier to use also that we'll look at. All right, so let's take a look at the chain rule. So we've got differentiable. This function with the independent variable of u is differentiable at this point, where u, the independent variable, is another function, right? So it's composition of functions. And g of x is differentiable at x. So the composite function, again, there's a couple ways to show that notation, is differentiable at x. And here are the two ways to do this. I'm going to eventually emphasize this way because this is sort of a smoother way to do this. So we've got the derivative, right, this little prime symbol, the derivative of f of g of x, and the answer to this question, when you differentiate this, it's going to be the derivative of f of g of x, but then times the derivative of the inside function. So we take the derivative of this like we normally would, but we multiply it by the derivative of the inner function because we have the rate of change of f and also the rate of change of g to consider. So the way that we've been doing it, this is more of a classical way that it's taught using Leibniz notation. It's a little clunkier, but it's more maybe of a methodical approach some students like because it's more of a step-by-step. So I'll at first show both of these ways, but eventually I'm going to go here because it's just a smoother way to do it. And this is the way that students tend to do it once they get a little more practice. All right, so we'll do it both ways first, though. So we'll start off, I'll do all these problems two different ways so we can see how they work. So first example, y equals sine of x squared minus 4. That's one that we were considering earlier. And I said, well, the rate of change of y is going to be the product of two rates of change. The rate of change of the sine function and also the rate of change of this inside function, the function that's inside the sine function. So the traditional way to do this is we would say, okay, y equals the sine of u, and u is that inside function. Right, so we think of it as a composition of functions. Then you would say, okay, dy du, that's the cosine of u, and then du dx is 2x. So once we split these up, we take the respective derivatives. So dy with respect to u, right, dy du, and then the derivative of u with respect to x, du dx. And then, according to the chain rule, dy dx is equal to the product of these two, which would be dy du times du dx, which would be cosine of u times 2x. But, of course, the original question didn't have any u's in there, so then we go and we substitute. So cosine of u, but what is u? Well, u is just x squared minus 4. So that gives us the cosine of x squared minus 4 times 2x. And remember one thing, this is the argument to the cosine function. This is not, so I can't distribute this through, right? That doesn't make any sense at all. This is the input to the cosine function, and then this is just times 2x. So a lot of times what you'll see is people will move the 2x in front. It just sort of avoids that confusion, but you don't have to. Either of these two, I mean, these are equivalent, of course. Either one of them is okay. So that's more the traditional way to do it. But let me show you the way that most of you will end up doing these. So I'm going to just write the question here again. So what we'll typically do is we'll say this. I'll kind of walk you through it. So we'll say something like this. We've got sine of something. So we're taking the derivative. So what's the derivative of sine of anything? Well, the derivative sine of anything is cosine of that same anything. Okay, the argument never changes. So we know this, right? If you have y is sine of x, y prime is cosine of x. Notice that the inputs don't change. It's x here, it's x here. It's always the case. If you have the sine of anything at all, when you take the derivative, you get the cosine of that same anything. So a lot of a pretty common beginner mistake is to take the derivative of sine and get cosine, and then take the derivative of this and get 2x. But the argument never changes, just like this, right? Everybody knows this. The derivative of sine is cosine, right? That's from 3.3. And the arguments are exactly the same. So they're always going to be the same. The derivative of sine of anything at all is cosine of that same anything at all. But then, once we do that, then we have to say, well, is this plain old x, like it is here? And since it's not plain old x, the chain rule says, okay, you also have to consider the rate of change of this thing. We multiply that together. So we go times x squared minus 4 prime. Right, so we need to take the derivative of this. Well, the derivative of this is just 2x. So this gives us cosine x squared minus 4 times 2x. And then again, you could probably, what you do is move it out in the front and get 2x times the cosine of x squared minus 4. And I'm just going to separate these. Okay, so one thing to keep in mind with these is that the big thing, which I've mentioned a bunch of times, I'll do it one more time, the arguments don't change, right? Derivative sine of this is cosine of that same thing. And then since that thing is not plain old x like it is here, we need the chain rule. Now technically we have the chain rule here too, but what's the derivative of x? It's just 1, so we actually don't do anything with it. So when the arguments are plain old x, we just take the derivative like we did in 3.3, derivative sine of x, cosine of x. But if this is sine of 2x, we need the chain rule. If this is sine of square root of x, we need the chain rule. Sine of x cubed, we need the chain rule. If it's not plain old x, we need the chain rule. All right, we've got another example here. Once again, I'm going to do this both ways, so you can see the traditional way and then the quicker way. So we've got cosine of x cubed. So what we have to think about is, what is the inside function? Right, because when we're going to set it up like with a composition of functions, we need an inside function. So this function, it's like a cosine, and then inside the cosine is x cubed. So this is the inside function. Cosine would be like the outer function. So if we set this up as a composition of functions, we could say, okay, y equals the cosine of u, and u equals x cubed. Right, so we'll do this the traditional way first. So then we say, all right, what about dy du? Dy du is going to be negative sine of u, right? Again, if that's the argument here, we take the derivative, it's the same argument. And then in this case, we're acting as if u is the independent variable, so we don't need the chain rule here, because if we use the chain rule, the derivative of u with respect to u is just 1. Okay, then we have u equals x cubed, so then du dx is going to be 3x squared. Once we have that, then we can say, okay, so then dy dx. What we're originally looking for, the derivative of y with respect to x, the independent variable. Well, according to the chain rule, that's just going to be dy du times du dx. That's equal to negative sine of u times 3x squared. Right, this is starting to sound similar. We can't use a u because the original question didn't have a u, it just had x's. But it's okay because we know u is just x cubed. So this is equal to negative sine of x cubed times 3x squared. Or negative 3x squared times the sine of x cubed. Right, because remember, this is the input to the sine function, or the argument to the sine function. This is not, this is just being multiplied by this whole thing. So often we'll just move it out in front. Okay, so now let's try it the other way. The other way is, again, let me put this one in black so it looks more like the original question, cosine of x cubed. Okay, so then if we're going to find y prime or dy dx, or however you want to say it, I'll just say dy dx. Well, just think of this. What's the derivative of cosine of anything at all? Negative sine of that same anything, right? So it's negative sine of that same anything. And then we just have to say, is this plain old x? Nope. This is not cosine of x, it's cosine of x cubed. So x cubed also has a rate of change. The chain rule says make sure to multiply this by that rate of change. So you multiply this by x cubed prime to get that rate of change. So we get negative sine x cubed times 3x squared. And then, of course, we can put that out in front. Sine of x cubed. Okay, so two different ways to do it. Same answer. Now, when you look at this one, it looks a little bit like the last problem, but it's really completely different. Because remember, when we use this notation here, it's a shortcut, but what it really means is this. So I'm going to extend this. What this really means is cosine of x cubed, right? That's really what this notation means. So when we have, like, you guys have seen this a million times, sine squared x plus cosine squared x equals 1. What we really mean is sine of x squared, right? Plus cosine of x squared equals 1. All right, so with that in mind, we look at this problem. Now the inside function is cosine of x, and the outside function is like a cubic, right? Like this thing cubed. So this time when we do this, we would say something like y equals u cubed. The cubic function is the outside function, and then u equals cosine of x. So then dy du going to be 3u squared, and du dx is going to be negative sine of x. So then if we use the chain rule, we say dy dx equals dy du times du dx. We get 3u squared times negative sine of x. One thing you want to be careful here too, let me put this in red. Sometimes students will do something like this, 3u squared, and then do something like this. And I got to tell you, it is way too easy to all of a sudden on the next line you just write this, and you get the wrong answers. Completely changes everything, right? So I would recommend never doing this. It's just too easy to, a few seconds later forget about the dot, and all of a sudden you have a subtraction problem, right? So I would say use parentheses in this case. It happens way too many times. I've seen it happen way too often. So you'd be better off just using parentheses to eliminate that chance of that happening. Okay, so then we've got 3u squared. Well, u is really cosine, so it's 3 cosine squared x times negative sine of x. And then we could just bring the negative out front and go negative 3 cosine squared x times the sine of x. Okay, that was the original way. So now let's do this. Do the same question. Y equals cosine cubed of x. Okay, and of course, really that means cosine of x cubed. So think if we just had y equals x cubed, it would be really easy. Y prime would be 3x squared, and we're done, right? The derivative here would be 3x squared from the power rule. Well, this one's going to be similar. It's going to be 3 this thing squared. And then the chain rule is going to kick in because this is not plain old x. But this acts like this. So when I figure out dy dx, it's going to be 3 this thing squared, right? So you get 3 cosine of x squared, but then since this is not plain old x like it is here, the chain rule kicks in. I need to multiply by the derivative of cosine of x. So then you multiply by the derivative of cosine of x, which is negative sine of x. So you get 3 cosine squared x. Notice how I just rewrote this. Cosine of x squared, I wrote it as this, cosine squared x. Then times the derivative of cosine of x, which would be negative sine of x. And then just pull the negative out front, we get negative 3 cosine squared x times the sine of x. Okay, so hopefully this is starting to make sense. And you can do these either way. Like I said, they both work. This way is a little quicker, and most of you will end up doing it this way as you get more practice. But let's take a look at something else. The power rule combined with the chain rule. What this is saying is we've got a couple of these rules we can join together. So if n is an element of the real number system, so n's just some real number, right? It's a real number, it's not a variable, it's a number. And g of x is differentiable, then if we take the derivative of u to the n, so we're taking the derivative of this power rule, but the difference is u might not necessarily be plain old x, it could be another function here, right? Well, we treat it the same way. So we're going to go just by the power rule. Like we've seen before, you go n comes down, n times u to the n minus 1 right here. But now we're saying this also, whatever this is, we have to multiply by the derivative of that because it's a chain rule, right? So it's just it'll come naturally once you do a few of these. This will just seem very natural, but it's just the power rule and then the chain rule kicks in. So for example, 6. If we were going to differentiate this, if we didn't have the chain rule, it'd be a lot of work, right? We'd take 4 of these expressions, line them all up, and start multiplying. It would work, but it'd be a lot of work. But with the power rule and the chain rule combined, the power rule says, okay, just like, okay, I'm just doing an example. If this said g of t equals t to the 4th, we just say g prime of t equals 4t cubed, and we're all done. Because in this case, this base is plain old t, so we don't need the chain rule. The derivative of t is just 1, so if we use the chain rule, we don't get anything different here. Okay, this is sort of like this. We're going to go g prime of t equals 4 this thing cubed, just like we did here. So g prime of t equals 4t squared minus 3t cubed. And then, since this is not plain old t, we also need to consider the rate of change of this inner function. And that's where we go times 4t squared minus 3t prime. Right, so then this gives us 4t squared minus 3t cubed times, and now we just use the power rule a couple times here, so we get 2 times 4, which is 8t to the first power, minus 3. Now there's no more derivatives. Now sometimes students will say things like, now do I need to multiply with the derivative of this? But you don't, right? Because look what we're doing. Just think, if this were the only question, take the derivative of this, you would just go, oh, it's a power rule, 8t minus 3. There's no chain rule here because this is plain old t and plain old t. So at that point, we're done. And then from here, if you wanted to, you could distribute the 4 through here if you wanted. Definitely not through here because that's cubed. But you don't have to. You can leave it just like this. All right, so now we are ready to try once again to find the derivative of a to the x. And if you remember, in section 3.1 we attempted this. We didn't have the chain rule yet though, and the chain rule is going to change this. So last time we tried to do this and we had a little bit of success, but we definitely did not find this. We defined the number e, and we ended up being able to find the derivative of e to the x, which was e to the x. But now we want for just a general base of any real number a. So that's what we're looking for now. And now that we have the chain rule, we're going to have a lot better luck. But first, let's review logarithms, because we're going to have to use some logarithms here. So let me write down some rules here. Basically, there's 3 of them that we should be aware of. And so logarithms, they really did change the world. It's hard to exaggerate how much they change things. John Napier, kind of an unusual guy, very talented mathematician and also a very unusual person. He did a lot with logarithms, with introducing decimals as opposed to fractions. And he lived in between 1550 and 1617. And he put together these rules of logarithms. And then Briggs came out, or Briggs was a little bit later, put together a large logarithm table. It took him about 20 years to put this table together. But basically, so these rules of logarithms make life easier if you're calculating, because instead of multiplying numbers, you can add, right? So logarithms simplify arithmetic operations. So instead of multiplying, we can add. So instead of log of a times b, it's equal to log of A plus log of B. The next one, instead of dividing, we can subtract. Log of A over B is equal to the log of A minus the log of B. So we're simplifying operations. And then this last one, instead of exponentiation, we can multiply. So this B comes down. It's equal to B times the log of A. So once Briggs put together this log table, which took years, I think in around 1624, he put together this table of logarithms, because once you have the table, then you can do all these things, right? So when astronomers were trying to figure out how large things were and how far away things were, and we were starting to put a lot of these pieces together, they would have to spend just endless hours with calculations, and logarithms changed all of that. And then the slide rule, most of you have probably heard of one or maybe even seen one, but probably hasn't used one. But they were actually used for about 350 years. From this time, slide rules are based on logarithms, and engineering students had them up until the 70s when electronic calculators came out. So they literally, for 350 years, logarithms were used with slide rules. So these rules were really, they changed everything. Almost like the way the personal computer changed the world, logarithms changed the world. It just made things much easier. It's hard to really imagine now, but it was a big deal back then. So just to practice these a little bit, just make sure these are fresh in our mind. What is the log of base 2 of 8? So remember what this means. What a logarithm says is, what power do I raise this base to turn it into this number? So in this case, it would be 3, right? It'd be 3 because 2 cubed equals 8. And also, for every logarithmic equation, there's an equivalent exponential equation, right? So this is basically saying 2 cubed equals 8. So the bases stay the same, base 2, base 2. So what about, if you typically don't use log base 2, you usually see base 10 or base e. Normally when you see this, it's understood to be base 10. So this is saying if there's a little 10 here, right? It's not really written, but it's understood to be a 10. So what power do I raise the base to get this number? Well, 10 to the first power is 10. So then if you have log base e of e, that is 1. And also there's a notation for log base e. So typically you don't see log base e, you see natural log of e. So natural log of e is 1, right? Because e to the first power is e. So we'll see this a lot. Natural log of e is 1. So we need to know that. And logarithms are used for things like if you're going to solve 3 to the x equals 15. So once again, just a little review. If we're solving an equation for x that's in an exponential spot, or for a power, it comes up a lot in finance questions where you have compound interest formulas and time is up here and you're trying to see, like, what if I pay an extra $20 a month on my car payment? How would that affect my loan? So you have to solve for a variable in the exponent location. So with logarithms, it makes it real easy because we have this rule here. So if we were going to do this one, what we could do is just take the log of each side. So you have like the log of 3 to the x equals the log of 15. And then with this rule here, this x can come down, so we're going to get, we'll get x times the log of 3 equals the log of 15. And then, of course, we want to get x by itself, so we just divide each side by the log of 3. These will cancel, and we'll get x is equal to the log of 15 over the log of 3. Now here, there's no canceling to do. We can't cancel the logs. We can't cancel and say it's log of 5. We just have to type in the calculator just like this. And the base doesn't matter. You could have done natural log here too. So you'd have natural log of 15 over natural log of 3. It doesn't matter. as long as they're the same base, we'll get the same answer. When you do this, you get roughly I'll just round it, I'll just say 2.5. Okay, so, which makes sense because 3 squared is 9 and 3 cubed is 27, so it's somewhere between 2 and 3. Okay, so we just need to review logarithms a little bit because we're going to use them for this. So to get back to this problem, we need to show one thing. All right, we need to first show this. Let's show that x is the same as e to the natural log of x. So if you put in your calculator e to the natural log of 7, it should tell you 7. So to show this, we'll do a quick little proof. Let's let y equal e to the natural log of x. We'll take the natural log of each side, so that the natural log of y equals the natural log of e to the natural log of x. Then we're going to use this log formula right here that says this b can come down, so we'll get the natural log of y equals natural log of x times the natural log of e. Right, we just brought this thing down. Now natural log of e, we know that's just 1. So then we have natural log of y equals the natural log of x. And of course the only way that could be true is if y equals x. And if y equals x, we can say therefore, because y equals e to the natural log of x, then x equals e to the natural log of x, which is what we needed to show. So we're going to need that. Okay, we're going to need that statement in order to do this. Okay, so since x equals e to the natural log of x, we could say, since this is true, we could say a equals e to the natural log of a. And then if we raise each of these to the power of x, we could say, all right, since I've got an equation, I can do anything I want. I'm going to raise this to the x power, and I'm also going to raise this side to the x power. And if that's true, then that means that a to the x equals e to the natural log of a times x. Right, because this is just like, remember in algebra class, we'd have something like x squared cubed. And we'd say, oh, we can multiply those. That's just x to the 2 times 3. So that's what we're doing to get from here to here. If I have this thing raised to the x, it's just the same as the base raised to natural log of a times x, just from this rule right here. Okay, so we need this. And then let's go and say that we want to take the derivative. Here's where the chain rule comes in. Okay, so we want to take the derivative of a to the x, which is the same as taking the derivative of e to the natural log of a times x, right? Because a to the x equals this from right here. Okay, so looking at this, let's do this. Let's move this up here a second. So we could say y equals e to the natural log of a times x. And then we could set this up this way. We could say y equals e to the u equals natural log of a to the x. Right, so we're going to set it up as a composition of functions. So then dy du is e to the u. Du dx, well, remember here, natural log of a is just some number, right? If you take the natural log and plug some number into it in your calculator, you just get a number. So this is a number times x. So the derivative of this with respect to x is just going to be whatever that number is. Right? Just like if this said u equals 5x, then you'd say, oh, du dx is 5, right? Just some number. All right, then we've got, according to the chain rule, dy dx is equal to dy du times du dx. And that is equal to e to the u times the natural log of a, which is equal to u e to the u is right here, so that's going to be equal to e to the natural log of a times x times the natural log of a. And then this thing right here, all of this. Well, if you look up here, we can see that's just a to the x. A to the x is the same as this. So I'm going to swap this out with a to the x. And we will get, the answer is a to the x times the natural log of a. So we're basically saying that the derivative here, dy dx, is just this. It's the original function times the natural log of a. So we can go back here and just say this. We can say, all right, the derivative of a to the x equals, well, we just found this over here. It's just a to the x times the natural log of a. So here is our latest and greatest differentiation rule. If you want to take the derivative of an exponential function, the exponential function comes back times the natural log of the base. Okay, so let's try one of these out. Let's say we've got a first example here. We want to take the derivative of 3 to the x. Well, according to our new rule, the derivative of a to the x is first a to the x. It comes right back, right? So this is going to be 3 to the x times the natural log of the base, which is 3. What about this, though? We know the derivative of this, right? It's e to the x. Will it still work here? Because this is a general rule, so it should work for any base, including e. So let's just see. If I put this into the formula, we get e to the x times the natural log of the base, which is e. And what's natural log of e? It's just 1, so it's e to the x. So we already knew from 3.1 that derivative of e to the x is e to the x, and it works with this formula too. Okay, but let me do a question that always gives us trouble. Let's say y equals, let's say, x to the 5th plus 5 to the x. And we want to find y prime. Okay, we have to be careful here. Sometimes these get mixed up. This is a power function, right? The exponent is a real number. So this is just a power rule. This is an exponential function. The exponent is a variable, right? So we need this rule here. So we have to be careful here, okay? So this is just something we've seen a bunch of times before. The derivative here is 5x to the 4th. We don't need the chain rule because the base is just plain old x, right? And over here, this is our new one. So we can't go x times 5 to the x minus 1, right? The power rule only works with power function. This is an exponential function. So the derivative of that is going to be 5x times the natural log of the base, and the base is 5. Okay, calculus fans, that should give you everything you need for 3.4. But remember, a couple things about 3.4, about the chain rule. Number one, it's really important. We have to understand it. And number two, it's a little tricky, sometimes a little awkward at first. It's a lot like riding a bike. At first, it's a little awkward, but once you get it, it's really smooth, and you remember it pretty easily after that. So that is the chain rule. So make sure you put in your time in this section. And as always, if you have any questions, just let me know.